Hello everybody, how y'all doing? Today we are going to be going over not double integrals, Taylor and Maclaurin series. They're pretty straightforward ones. If you're good with patterns, you should be fine. This is a recall, so I'm just going to skip it. How do we derive such formula, which includes more terms? Our goal is to approximate. Again, I'm going to skip all this first page. You don't need to know any of this stuff for the exam. This is the important stuff you need to know. Right? So this equation is given, but the most important part is this section right here. So actually, I'm gonna highlight. So this is actually the most important part that for this. The rest of it is mostly plug and play, except this section, which the difference is here is between Maclaurin and Taylor. That's the only difference. So between Maclaurin and Taylor, this is about the only difference, and for general, this would be what you're worried about. The rest of it will most likely stay the same. This sometimes will change from 0 to 1. But anyways, the hard part is your f to the NA. And so what does f to the NA mean? All right. And so we'll go right into an example, but before we get into that, if we consider just the first n terms in the polynomial, then we obtain the nth degree. Something, a special case that occurs often is, okay, so what a Taylor and a Maclaurin series basically are is telling you a simplified way of doing something that is repetitive. Okay, so for example, if I integrate, or if I derive, so if my f of x was e to the x, and I derived it, I will get e to the x again, and e to the x, and e to the x. And so there's a way to write this in terms, in a series term, something like this, that it just tells you this pattern can be represented using this formula. Okay, and so what you're trying to learn here is how can you write this function, or this whatever you want to call it, the series form, to represent this pattern. Okay, so how can we represent these patterns mathematically? And so the difference between the Maclaurin series and Taylor's series is that Maclaurin is at a equals 0. There you go. Actually said it. A special case that occurs often is when a equals 0. So we give it a special name, the Maclaurin series. That's the only difference between Maclaurin and series. Maclaurin and Taylor is that Taylor, the a is not a non-zero, and Maclaurin is a at 0. There's some other things that happen when a is 0, but for now, the only difference you want to remember between Maclaurin and Taylor is that when a is 0, it's Maclaurin. When a is a non-zero, it's a Taylor. All right. So for factorial, what you need to know is that it's a non-negative integer. Okay, and n factorial. So what it says is that, well, here, is the product of all positive integers less than or equal to n. So n is inclusive. All right. So if I have 5 factorial, it'll be 5 times 4 times 3 times 2 times 1. Not times zeros. You don't do times 0. Okay? All positive integers. Okay? And so my 0 factorial is by default 1. If I do 2 factorial, it's just 2 times 1, which is 2. Right? And so that's what factorial means. Alright, so now find the Maclaurin series for f of x equals e to the x. And so as soon as I say Maclaurin series, you know a equals 0. Okay? And so how can we find it? What you want to do is you want to derive until you see a pattern. Okay? So as you can see, f of x equals e to the x. F of first derivative of x equals e to the x. F of second derivative of x equals e to the x. And as you can see, this doesn't change. And if we take our formula right here, and well, before we do that, let's do it as 0. So we know f, so at a 0, right, because a equals 0, so at a 0, this equals 1, e to the 0 is 1, right? And so f double first derivative at 0 equals 1, f second derivative at 0 equals 1. And so now what we're trying to do is, if I can grab this formula, let me write it. So what you say is your sum, what can I write it here? My sum from infinity to n equals 0. By the way, your n's are these derivatives. This is n equals 0, n equals 1, this is the first derivative, n equals 2, second derivative. All right. So from n0 to that, we're going to take the function. We have f of n at 0 over n factorial. And as you can see here, the difference here, in your Taylor, you have a -1. In your Maclaurin, you have just x to the n. So see here, x minus 1. Here, minus a, this is x to the n. And the difference is because your a in the Maclaurin is 0, right? And so it goes away. You just have x, and you just raise it to the n, all right? And so we have x to the n. Now we know our x. Well, not our x. We know our function every time it goes to 1, and it keeps going to 1, and it keeps going to 1. And so our f at some n, at some derivative, at 0 will always equal 1. And since we know that, we can say the sum from infinity to n equals 0, 1 over n factorial x to the n. And now I just take this on top if I want to simplify, and this will just be n equals 0, x n over an exclamation mark. Okay, and so I hope that clarifies it. Well, we're gonna go to something more complex, which you'll really see the use case of this. And so if I go here, and then now we're finding the Taylor series. So if I'm gonna write the equation here, and so infinity n equals 0, and I have f at n of some a over my n factorial times my x minus a. All right. Now I do know my a's too. All right. So my f n at a, well, now it would be at 2. Okay. Now I gotta find my f at n. And how do I find that? Like I said, we're gonna derive until we see a pattern, right? What f at n at a equal to this means is, what is the pattern here? And so what's the pattern here? So we have f at x equals 5 e to the 3x, and then my second derivative, my first derivative, sorry, this would be, don't simplify it, write it how it is. So I have my 5, and then when I derive, the 3 comes down, and I still have e to the 3x. Now if I do it again, right, I get another 3 now, e to the 3x. Again, this is the last time I'll do it, since I'm pretty sure you guys can see the pattern that I'm looking at. E to the 3x. All right, so this is n equals 0, n equal 1, n equals 2, and then n equals 3. So what are we looking at? First, we know that we'll always multiply by 5. Okay, so my f at n at 2, well, first actually, let's plug in our 2, and so let's do that. So f at 2 equals 5 and e to the 6, and then f first derivative at 2 equals 5, 3, e to the 6, and so on. Okay, so now that we have this, what we will say is f at n at 2 equals, what do we have? Every time it multiplies by 5. So my 5 stays, okay? But every time as n increases, my 3 increases. So what can we say? We can say 3 to the n, all right? Because when n is 0, this turns into 1, so it goes away. When n is 1, this is 3. When n is 2, 3 times 3, which is 3 squared, right? When n is 3, 3 to the 3 is the same thing as doing 3 times 3 times 3, right? So that represents that. And then we have my e. What is my n here, right? So we have 3 to the x. Now it's always multiplied by 3. And we know at a2, so we're taking at a2, this will always be 2, right? And so if we're writing our fn at 2 equals, it's 5. So I'll do it. So it's 3 to the n times 5 times e to the 6. And so you take that and you plug it here. So now we have our sum. Ooh, look how beautiful that looks. Right? And we have 3 to the n times 5 times e to the 6 all over n factorial x minus 2. All right, and so that's really how you do it. Some patterns will look a little bit more complicated or a little bit more challenging, but we'll go through most of them. All right, so moving on to the next step, which is find the Maclaurin series. So we know when the Maclaurin series a equals 0. And so if we do our equation, we have infinity, n equals 0. We have f at n at 0 all over n naught, or n factorial, x to the n. All right, and so now we're trying to find out f of n. We want to integrate this until we see a pattern. And so let's do that. We have f at x equals 7 plus 4x and negative 1, right? What I'm going to do here, I'm actually going to do it at 0 right away, okay? Since there's no point in doing this part. So if I take it at 0 right away, what I'll get is first 7, then negative 1. Then I will get, if I derive this, right, what I'll get is negative, so this will come. Oh, actually, yes, I might have made a mistake here. Yes, I made a mistake here, because when you derive this as a 7, this would just turn into 0. So you actually do have to do the 2 steps. Is deriving it like this, then you plug in your 0. Okay, so good thing I caught that. Okay, so for this one is just 7 plus 4x. Right? Now when I derive it, so this is n equals 0, 1. And then when I derive this, what will I get? You guys know, this will, the negative 1 comes in front, so the negative comes in front. Then I will do my 7 plus 4x. Then you gotta times it by the derivative of the inside, which is just 4. Okay? Now, second derivative. I'm not really seeing a pattern yet. If you guys are, then that's good. Obviously I have my negative 2 here. Now I gotta bring this down, so I got now positive 2, right? 7 plus 4x to the negative 3, 4, and obviously now I still gotta multiply by the derivative of the inside, so that's another 4. Now my third, I got 2 times 3. This is obviously negative, and then 7 plus 4x times 4 times 4. These are from before, and then I gotta add one more 4. And I think now we're seeing the pattern, is that as we're going, it's going positive, negative, positive, negative. Okay. Also, as we're going, when n is 0, there's nothing. When n is 1, it's just 1. But when n is 2, I get 2. And then when n is 3, I get 2 and 3. Okay? And then also realize when n is 1, I get 1 4. When n is 2, I get 2 4s. When n is 3, I get 3 4s. Okay? So now how do we represent this? There's one more thing. And as you can see, this also increments backwards as we go down the ends. And so our f of n at 0, we haven't done the 0 part, but we'll get to it. But now the question is, well, okay, how do we do this? Where do you start first? So the first thing you want to do is start with the first pattern. All right. So what is the first pattern you want to do? We can do the 4 since it's the easiest one. Now we know at n0 equals 4, at n1 equals, at n0 there's 1. So this is like an imaginary 1, let's say. At n equals 1 is a 4, at n equals 2 is 2 4s. So we know my 4 increments as n increments. And so you see, when my 4 at 0, it's 1. When my 4 at 1, it's 4. When my 4 squared, it's 4 times 4. And that's the same thing, 4 times 4. And so you see, that part we got right. Okay, so that's my first pattern done. And you can just, cross it out. Like we finished this part. Okay, now the second part. We know our 7 plus 4x is, goes downwards. So you see, when n is 0, so when n equals 0, we get negative 1. When n equals 1, we get negative 2. When n equals 2, we get negative 3. What's the pattern we see here? Okay, so we see that n is always minus 1. So the negative term of n, minus 1. So you see, if I take this n equals 1, and I turn it into a negative, n equals negative 1, and I minus 1, I get negative 2. If I do the same thing here, n equals negative 2 minus 1, negative 3. And you see this matches this. And so what I could say is, this is the same thing as saying, depends on how your brain works. My brain works this way that I just showed you. The other way you could do it is if you do n of 1 plus 1, and then you turn the whole thing negative, you get negative 2. And if you take n at 2 plus 1, and you turn it negative, you get negative 3. Right? And so this is saying n plus 1, n plus 1, and then you can turn the whole thing negative. Or, so I'll zoom in here, I'll make this clearer. So you can make n plus 1 and turn it negative. Or you could do negative n minus 1. And that's the same thing. Okay? And so that's our second part, which is done. Okay? Now, how do I represent negative and positive? I see negative, positive, negative, positive. Now, if you do negative 1 to the 0, you get a 1. If I do negative 1 to the 1, I'll get a negative 1. If I do negative 1 to the 2, I'll get a positive 1, and so on. Now, if your first term, my first term is positive, then, and my second term is negative, then I will use this to the n. Negative 1 to the n. You know, when my n is 0, it's positive. When my n is 1, it's negative, and that's the same thing we did here. If it's the other way, let's assume this was negative and this was positive. How do you represent that? What you can do is, so let me get rid of this. What you can do is you can do negative 1 n plus 1. Okay? And so this will work the other way. When n is 0, let's assume this number is negative. When negative 1 and n is 0 plus 1, you see now I get negative 1. Before I was getting positive when n is 0. And then when negative 1 and n is 1 plus 1, this becomes 2. And so I get positive. And you see now I flipped it. Now it goes negative positive instead of positive negative. And so these are the two ways you can switch in between. All right. And so let's write that down. Then what we need is a negative 1 to the n, because it starts positive, then it goes negative. Okay. So we finished that. Now the second thing is we want to represent this. How can we represent that? Now what you could do is you could do I have to think about it for a bit, but now I got it. So you could see this is a factorial. See? So when n is 0, this equals 1. Because you see, it doesn't multiply by 0 because this whole thing will turn into 0. When n is 1, the answer is still 1. So see, it's still 1. You have a negative 1 here, and you have like a positive 1 here. Okay? When n is 2, you get 2 times 1, which is the same as just saying 2, right? And that's how we have only 2. When n is 3, we get 2 times 3. Or, well, technically would be 3 times 2 times 1. And then if we go n4, I bet you, because you see this 4, it will come down. And so I will get at n4 equals 4 times 3 times 2. And so now the last thing is n factorial. Okay? And so that is really how you get Taylor series. If I rewrite this here, so actually we write this here, on my f at n at 0 equals, we have an n factorial. But actually first, let's put the negative 1. So negative 1 to the n times 4 to the n times, I'm thinking, can we combine these into one number? What if I take these two and I do negative 4 to the n? Wouldn't that technically also oscillate between negative and positive? And it will also do the multiplication that is doing here. You see, that's one way to do it, but I'm not going to do it because I don't think they're asking for you to simplify to this extent. So I'm going to leave it as is. Okay? So anyways, so 4 to the n. And we also got our n naught, or n factorial. And we also got our 7. Now notice, if I do plus 4x to the negative n plus 1, okay, I have an x here, but my function is at 0. So what you do is actually you don't put your x here, you'll sub it in. And so when I sub it in, this will become obviously 0. And 0 times thing is 0. And so what happens is this goes away. And it just becomes 7 to the negative n plus 1. Negative n plus 1. Okay? And now you just take this, sub it in here, and that's about it. So I'll just do it. I have infinity, n equal 0 equals, right? And naught, and you'll notice something. These two would cancel out. And so you'll get this times this, and that's about it. Alright, now so far we've found Taylor and Maclaurin series for very simple functions, but we can use these results to find the series for more complicated functions. We have, okay, so for this part, really, because this is a Maclaurin, you just gotta sub them in. So the pattern here is, so since we have your sum here, so it tells you for this is your series, right? Now what if I change my x to the 2? Then what happens? That's all that happens. And how does that work? All you gotta do is you take this and you sub your new x. So my x is squared. So instead of this x, I have x squared to the n, which just becomes x to n, right? And so that's how you do it. Now if you have something like this, you could still do the same thing. So you could do your summation. I'm not gonna write my summation anymore, but let's say x. Now this we know it becomes 2n over n factorial, and now you have your summation, and you just keep your x3 here. Now if they multiply, right, it would be x 2n times x to the 3, which is the same thing as x 2n plus 3. And so that would be your new factorial. Your new series. Pretty simple, right? And now that would be for this part, and this would be for this part. All right. And so given the Maclaurin series, this sine is this. Now what if I have sine 3x? What am I supposed to do? All you gotta do here is just sub in your x. So you keep this x on the outside, right? And then you'll have negative 1 n all over 2n plus 1. Not, and then you just sub in your x, so it just becomes 3x. Right? And the thing is, you could technically multiply your x in, but that would be a little more complicated because when you multiply it, you'll have to multiply this in here. Then you'll also have to multiply this in here. And so it changes things up, but you could leave it as is like this and it would still be right. Okay? And that's about it for Maclaurin Taylor. I hope you guys learned something, and thank you for watching.